welcome to our first lecture for chapter 14. This is chemical equilibrium. It's quite a bit easier than last chapter, I feel. Hopefully you'll agree. Equilibrium in chemistry. It's important to note that equilibrium does not mean stopping. Equilibrium means there's no observable change as time goes by. Chemical reactions, a lot of them are reversible, and that doesn't necessarily mean that just because there's no observable change doesn't mean molecules have stopped changing. It just means we don't observe that change. So when do we achieve chemical equilibrium? When the rate of the forward reaction is equal to the rate of the reverse reaction. So the same rate we're forming products out of reactants, we're also forming reactants out of products. So it doesn't look like there's a change, but of course at the microscopic level there's a lot of change. If that's the case, then the concentration of our reactants and products will probably remain constant. And so that is the physical equilibrium here. Liquid water goes to gaseous water. The same rate gaseous water goes back to liquid water. Chemical equilibrium, dinitrogen tetroxide goes to nitrogen dioxide at the same rate that nitrogen dioxide goes back to dinitrogen tetroxide. So it doesn't look like there's any change. Here's an example of that same reaction we just talked about. If we start with that NO2, then our graph might look like this. The NO2 starts to decrease, the N2O4 starts to increase, and over time we get to a point where the N2O4 stops increasing, the NO2 stops decreasing, and we call that point equilibrium. If we were to just start just with dinitrogen tetroxide, that would start to decrease, and the amount of nitrogen dioxide would start to increase. Eventually we get to a point where N2O4 stops decreasing, NO2 stops increasing, we call that point equilibrium. If we start with both, here we started with our N2O4, started to increase, our NO2 started to decrease, and eventually we got to a point where they weren't changing, and we call that point, again, equilibrium. So when we look at this system, we can see our concentrations will change till they get somewhere in the middle. But those middles never really line up that well. So if we divide our product by our reactant, that doesn't really line up that well either. But if we divide our product squared by our reactant, we get a constant. Perfect. That is our constant. So it's called an equilibrium constant. And the reason we get the squared is because of this. Products divided by reactants makes a little bit of sense. It's what you're getting divided by what you're starting with, but the 2, our coefficient, becomes the superscript for squared here. K is equal to NO2 squared. We take this guy, put it at the top, divided by N2O4. Then you can plug in any of those values, and you'll always get 4.63, or something very close to it, times 10 to the negative third. And so here's the generic equation. Coefficient A plus coefficient for B is in equilibrium with a coefficient for C, and the same thing for D. So when you write that, it would be the concentration of C times the concentration of D. And both of those are raised to the power of their coefficient. It's important to note that it's products divided by reactants. You do the same thing with your reactants. It's very easy to write these. We'll get plenty of practice with them. We call this the law of mass action. I'm not going to spoil that for you. I'm going to make you find it in your book because it's one of our questions. And so here's how we write that equilibrium expression. So if you're looking at this and you say, okay, if K is much greater than 1, and it's products divided by reactants, if K is a large number, then our products must be favored. This equilibrium must be shifted pretty far towards the product side. And you'd be right. So the equilibrium would lie more towards the right, more towards the products. We'd favor our products with that equation. Doesn't mean it's not an equilibrium. It just means at the rate we form a little bit of reactant, we form a little bit of product. And the product happens to be quite a bit more. Now if K is very, very small, we have a very small concentration of reactants over a very large concentration of products. Whoops. Excuse me, I'm sorry. A small concentration of products over a large concentration of reactants. And so we get a very, very small number. So it's going to take our equilibrium quite a bit to the left. So we know that equilibrium would favor reactants. It might look something like this. So our equilibrium constant tells us a lot about our equilibrium. So there's homogeneous equilibriums, and that's all of our reactant species are in the same phase. So this is a gas, everybody's a gas, it's homogeneous. You write it the same way. Take 2, make it a superscript, that kind of stuff. So that's Kc, equilibrium constant. This is Kp, pressure. Now pressure only matters if you're a gas. Now because these are both gases, we write them both. The partial pressure squared, still important, still comes from here, of nitrogen dioxide over the partial pressure of N2O4. In most cases, the equilibrium constant is not going to be equal to the pressure constant because most of the time not everything's going to be in the gas phase, and if it is, they don't all necessarily have the same molar masses, so they're not going to have the same gas pressure. Kind of takes us back to that whole PV equals nRT thing, but you probably don't want to revisit that. So, take my word for it. Kp is equal to Kc multiplied by RT. R is the universal gas constant, 0.0821 liter atmospheres per mole Kelvin. To use temperature, absolute temperature in Kelvin, so take your temperature in Celsius, add 273.15, and we're raising it to the power of delta N. Delta N is the change in gaseous moles. So the moles of your gas products, in this case it'd be 2, minus the moles of gaseous reactants, which would be 1, so it'd be 1. It's not too bad. So, homogeneous equilibrium, here's one. Aqueous means dissolved in water, liquid, dissolved in water, dissolved in water, so basically this whole thing's liquids. So we can write our Kc for this is our products divided by our reactants. Perfect. Now water is a constant in this, and so we can write it this way. Water is kind of like a solvent. We don't write solvents in equilibrium expressions. We don't write solids in equilibrium expressions. So go ahead and take note of that. No solvents, no solids. So since water is pretty much a solvent, if you look at this, we don't really need water to make this kind of thing work. It's just sort of the medium that it's occurring in. Then that's the reason we're taking water out of that. So that's going to be kind of equal to this Kc of water. So general practice, we don't include units for our equilibrium constants. They don't have any sort of labeling unit after it. So let's look at a problem. Equilibrium concentrations for our reaction. We're going to take carbon monoxide, we're going to take chlorine, we're going to form COCl2. So it'd be a good idea to write that equation out. We're doing this at 74 degrees Celsius. Here's our concentrations in molarity, molarity, molarity. Calculate the equilibrium constants. So we write the equation, we make sure it's balanced. And if it is, we progress from there. So we say, okay, these are all in the gas phase, which is nice. So COCl2, put that products divided by our reactants. We take the numbers they give us from the problem, we plug those in, multiply them out, and we get 220. Easy. Now for Kp, we take the 220 from here, we take R 0.0821, temperature 74 plus 273.15, delta N would be what? 1 mole of gas minus 2 moles of gas, -1, something like that. There we go. So, then you can solve it. Kp, plug those in, 7.7. So, let's look at another one. Equilibrium constant Kp for the reaction. 2 nitrogen dioxide gas goes to nitrogen oxide gas and regular old diatomic oxygen gas. The Kp is 158. Our temperature is 1000 Kelvin. It's nice, they gave us Kelvin, we don't have to convert. What's the equilibrium pressure of oxygen? If the pressure of nitrogen dioxide is 0.4 and pressure of nitrogen oxide is 0.270. Oh, so that's easy. They give us the pressure for the whole reaction and the pressure for this guy and the pressure for this guy. Find this guy. So not so bad. We just set it up like this. Our pressure is equal to our product, pressure of NO squared, pressure of oxygen divided by pressure of NO2 squared. Sub the values and they give for it. Here they rearrange the equation first, and that's fine. You can rearrange the equation first. You could plug all your values in from the problem. 158 goes here, pressure of NO2 goes here, it's 0.4 squared, pressure of O2 is what we're solving for, pressure of NO is 0.270 squared. Solve for that guy. If you want to rearrange it first, go for it. Here's what they did. Took all those values I just told you, put them in. Should be about 347 atmospheres. So let's look at heterogeneous equilibria. A little bit tougher, but really not that bad. Reactants and products are in different phases, so solid, liquid, gas, that kind of stuff. So here we have a solid, calcium carbonate goes to solid calcium oxide, gaseous carbon dioxide. So when you write that, you would want to write it like this, product divided by reactant. But you remember mentioning earlier that we don't write solids in equilibrium expressions. We just don't. So you'd actually just write it like this. Calcium carbonate's constant, calcium oxide's constant. Kc is equal to just CO2. That's it. You can't write solids. It's gotta be liquids or gases. And so you could say our Kc prime is calcium carbonate divided by calcium oxide, but again, that's a constant. So our Kp is just the pressure of CO2, and our Kc is just the concentration of CO2. That's it. So the concentrations of solids and pure liquids are not included in the expressions for our equilibrium constants. And so that's why we leave these guys out. So we look at this here, we see that calcium carbonate, calcium oxide, these solid masses are changing. A little less calcium carbonate, or rather, sorry, little more calcium carbonate, a little less calcium oxide, but those solids don't affect the pressure in the solution because the pressure is dependent upon a gas. So you can see your little mercury meter here is not moving at all because the pressure inside is not changing. So our pressure of CO2 is our constant here. It's our gas pressure constant. And so the pressure of CO2 does not depend on the amount of these solids in here. So let's look at a different one. What do we have here? Ammonium and some sulfur gives us ammonia, hydrogen sulfide, gives us a temperature, gives us a pressure of each gas at 0.265. So that means this guy is 0.265, this guy is 0.265. Calculate Kp and Kc. So there's a few ways to do this. You start with Kp, you say, okay, it's only the gases. So our product, it's a gas, divided by, well, I can't write that, it's a solid, so it's just the product of these gases. We don't have to square them or cube them because there's no 2's or 3's in here, so that's nice and easy. And it said they were both 0.265, so we take our 0.265, multiply by our 0.265, we get a Kp of 0.07. That's it. So now we gotta solve for Kc. They give us a temperature. We've got moles of gas at 2 minus moles of gas at 0. Going to be delta N at 2. R is 0.081. Temperature is 295 Kelvin. Solve for Kc. You may rearrange those first. If you like, you can do that as well. I don't. Doesn't make it right or wrong. I just don't rearrange it first. I just kind of plug the values in and then start my math. So they find their Kc to be about 1.20 times 10 to the negative fourth using this equation right here. So hopefully you find that pretty doable. We'll practice that in class. Here's kind of a weird concept. We're going to look at two reactions, equilibria involving multiple reactions, and it's actually not as hard as you'd think. Here we're looking at two reactions. We get Kc prime and Kc, I guess you'd call that double prime, something like that. So the first one would be, CD over AB, products over reactants. Second one would be EF over CD, products over reactants. But you'll know that CD's, being consumed, so it's kind of like, well, can that stuff really hang around? How does that work? Because Hess's law tells us that stuff can kind of cancel out if it's on both sides of the arrows. And you'd be right. Your overall reaction is A plus B yields E plus F. And that's going to be our Kc, our equilibrium constant for the whole reaction. And so it'd just be EF over AB. And the way we get that is, if you multiply these together, you actually get the same thing. So we can say that our equilibrium constant of multiple reactions is equal to the sum, the product of the equilibrium constants of the individual steps. And so if a reaction can be expressed as the sum of two or more reactions, then the equilibrium constant for the overall reaction is given by the product of the equilibrium constant of the individual reactions. And so if you multiply this guy by this guy, you'd have C times D divided by C times D. If you multiply these two, you'd be left with EF over AB. And EF over AB is exactly what you get. So that's how we get this law. Let's look at this one. We got a gas turning into a gas. I feel like we've seen this before. Could be wrong. They give us a K to start with. Then we have another reaction. This gas, this product, going back to this gas. And the K for that is 1 over K. Sure. 216. So what this is showing you is if you have the reaction for this reactant to product, and you have the K for that, and they ask you, well, what's the equilibrium constant of the product going to the reactant? If you flip the reaction, then you flip the constant. It's 1 over the old constant. And so it's very easy. You just take 1 divided by 4.63 times 10 to the negative third, you get 216. So, when the equation for a reversible reaction is written in the opposite direction, the equilibrium constant becomes the reciprocal of the original equilibrium constant. We can solve for that, and we will. So, how do we write these? You've kind of picked up on a few of the rules already, but here's an overview. Number 1, the concentrations of reacting species in the condensed phases are expressed in molarity, moles per liter. In the gaseous phase, the concentrations can be molarity or atmospheres, either one will work. The concentrations of pure solids, pure liquids, and solvents are not written in equilibrium constant expressions. The equilibrium constant is a dimensionless quantity. It's not decimeters or molarity seconds, no units. In quoting a value for the equilibrium constant, you must specify the balanced equation and the temperature, because the equilibrium constant is dependent upon both of those. And then finally, if a reaction can be expressed as a sum of 2 or more reactions, the equilibrium constant for the overall reaction is given by the product, so multiplying the equilibrium constants of the individual reactions. And that is where we will stop for today.